Good evening, Data 100. It's so good to be back after a while. It's been some time. I've been missing lecture and all of you. Today my plan is to cover a very practical and a very fun lecture. So half of it we're going to talk about cross-validation. This is very practical. And then half of it is going to be regularization, which is going to be even more practical. So let me tell you the story of like what we're actually going to be talking about. So in lecture 14, you remember a long time ago, it was the last lecture before the midterm. We basically had this idea. We said that, okay, we're gonna go do feature engineering, put together a lot of cool features, and we're gonna do modeling. So the more features we added on the x-axis, you see this model complexity. So the more feature we add, then the model is gonna get more complex. Then the idea was that the more features we add, then the model is going to learn better features, is going to have better signals. So it's the error on the training is going to be reduced. So that's the blue line that you're seeing. But then we also talked about the fact that, okay, if you basically go and take more samples from your population, so anything that you have not seen in the training data. So the blue one is a training error, then the red one is what we call out of sample or the test error. So if you basically try to sample some more from the same population and take a look at the error, you're seeing that, okay, like it's not going to be perfectly matching the same training error, but it also has a similar pattern before that dashed line. So before that dashed line, so as the training error drops with the model complexity, then the test error is also dropping, meaning that we're actually using good features in order to do modeling. But there is a point that the error on the out of sample kind of data set or the test data set is going to increase. So this is going to tell you that the feature engineering that you kept doing in the training data was actually overfitting to the training data that you had. So you were basically trying to fit to the noise of the training data as opposed to the actual trend in the training data that you have. So what we're going to do today is we're going to actually try to find out this sweet spot here. So we're going to find out, okay, like what is that sweet spot? What does it mean for us to have different kinds of errors for in sample training or out of sample, which is the test error, and how can we actually simulate the process so we can make sure that we're not overfitting to the training data during the process that we have. So the two questions that we had was that how can I actually simulate unseen data? This is the first question, right? Because you might be asking that, okay, like if you have data points and you're using all of those data points in your training data, like we give you a data frame, you do the modeling. So you have a model. So you used up all of the samples. How was I able to even get the red line in the first place? So what does it mean to sample from the test data or have a test data? So what we're going to actually take a look at is how we can systematically build something like that so we can have a notion of when we're going to overfit to the training data. But then also the second question is the idea of model complexity and actually limiting the ability of the model to keep making the model more complex so that it overfits to the training data. So this is going to be the version of the same plot that you had seen previously that I'm going to use in today's lecture. So what we're seeing is on the x-axis, I'm still seeing model complexity. So the complexity starts from the model that is very simplistic. So hopefully when the model is not hopefully, but when the model is super simplistic, we would say that the model is underfitting to the data. So it's not learning anything, it's not learning enough, so it's underfitting to the data. It's not fitting well to the data. So the complexity increases and increases and increases. So what you're seeing is that the training error keeps decreasing. And as we increase the complexity, then the model is going to overfit to our training data, which is the same thing that you saw in the previous slide, that overfitting means that we cross that dashed line and the error on the test data will keep increasing after that point, meaning that we overfitted to the training data. The other thing that I want to point out here that's going to be helpful is the variance. So look at the variance plot. So I now have a different line here, and I'm saying that, okay, the variance is going to start from a small variance, and then it will go and increase as I increase the model complexity. So the easiest way that we can make sense of why the variance is an increasing function is that, okay, like when your model is super simplistic. So what's the simplest model? It probably is a constant model, right? How would you calculate the variance? Like if you change the input to your model, would the output of the model change or not? So it would not change. So there's no variance in the output. But what's happening is that if you keep increasing the model complexity with this small change in the input, so for example, if the input was 1 and now you're passing 1.1, because the model is now so complex, it's unpredictable. So the output can drastically shift or change as you make various small change in the input. So that's why the variance is going to increase as we increase the model complexity. We're going to go deeper into variance, calculating variance, making sense of model bias and variance in the next couple of lectures, but I just want to make sure that we're all on the same page about what's happening here. We're looking at model complexity. We're interested in this sweet spot right here. We want to make sure that the training error is as small as possible before the point that we hit overfitting. So we want to have a balance between underfitting and overfitting in our training. So in the first half of the lecture, I'm going to actually talk about cross-validation. How can I simulate the unseen data for you, right? Because the unseen data is like reporting an error on the unseen data is just like probably not defined, right? So I'm going to tell you how I'm going to simulate a process that we can have unseen data in our process. And we're going to go through a process that's called cross-validation. And then in the second half, I'm going to talk about regularization, making sure that the model is complex enough, but not too complex. So that's what's going to come your way. So let's get started with the first thing. So the first thing is that assuming that I have a training data with only 5 samples, this is 5, or 6, or a little bit more. But anyhow, with just a limited number of samples. So there's this point, this point, this point, there's a couple of points here, and there's this other point. So if I go ahead and fit a very complex model, so what you're seeing is this kind of a higher order function that's fitted to the data. What you can see is that the training error is 0. There's no error because we were able to perfectly go through all of the data points. But is this a model that has a high variance or low variance? Again, what I want you to take a look at is if I change the value, for example, if you're looking at this specific data point for the input of horsepower being whatever, that's like 110 probably. If I increase it slightly, and if I look at this other sample, would you expect to get a different output, or would the output drastically change or not? So this is an example that we would say that by slight changes in the input, we're drastically getting a different output. So the model is a high variance model, as we're seeing here. So again, like you're looking at this is probably a 3rd order or 4th order polynomial. A 4th order polynomial is not going to be a good model complexity for us when we're fitting to 5 or 6 different data points, because we can technically go ahead and perfectly match to all of the data points. So this is what we mean by controlling the complexity and controlling the variance to the sweet spot so that we capture the details, but we don't capture all the noise in the data. So it looks like that here we're capturing the noise. How do I know that we're capturing the noise? If I go ahead and take a look at the entire distribution, so look at all of the samples that I have here. If I had the chance that I could go out and collect more data, and in fact, if the data was showing that kind of pattern, and I fit the model that I trained on those 5 or 6 data points, you can kind of see that that model is not reflecting the correct trend or the pattern in the data, right? So that's where we would say that we overfitted to only 5 or 6 samples that we had, but the actual trend in the data is different. This is the case that we're going to get a perfect prediction on the training data, but a horrible prediction on unseen data. So these data points were supposed to be unseen. So what we're going to try to do is that we're going to say that, okay, hypothetically, if you had this original data set, how could you simulate unseen data so you can kind of do a sanity check so you don't get into the kind of the issue that you're seeing here and get surprised a little bit. So the data set that we're going to work on is the same data set that you saw in the feature engineering lecture. It's going to be horsepower as features or different orders of horsepower, and then we're going to predict mile per gallon in the vehicle's data set. So the idea of simulating unseen data we're going to call that test data. So what we will effectively do is that we're going to separate one chunk from your data frame. So we're passing you the data frame. So you have your initial data frame with all the features and whatnot and all of the target values. What you need to do is to go ahead and not consider the test set when you're fitting or training the model. So just set aside the test data from your original data set. This is the way that we're simulating unseen data. We're going to call this a test set. But there is a caveat here that you're allowed to only use the test set only once in order to compute the error in the model, right? Only once, because when you test it on the test data and you're not happy with the result on the test data, you're not allowed to go back and redo the modeling. So the idea was that this test set should be the holdout set, unseen data. You should not make any modeling decision based on the test data. That's why you can only see it once. So we already realized that there are issues here, that when we only see a test data only once, there might be issues. Like there is no way that we can have a feedback loop of improving the model. What if I want to improve the model? We're going to come back to that in a little bit, but I just want to show you that generally unseen data, a holdout set that we're talking about is going to be this test set that we're going to create. How do we actually do it in our framework? Scikit-learn has train test split function, which can directly do that for us. And I'm going to show you in a little bit in the demo how we can actually use it. So what it gets is it gets the entire data set. So it gets your design matrix. Remember design matrix from OLS? So it gets the design matrix. It gets the target variables, all of the y values that you have in a vector. And then what it will do is it will basically try to split the data set into two parts. So we will have one portion that we're going to call it training set. So this training data is the data set that you're going to use for fitting the model. Once you fit the model, once you're done with all the parameter tuning, deciding about hyperparameters, deciding about the learning rate that you want to use, and everything is done, then what you will do is you will go ahead and test the model that you created on the test data only once. And I want to emphasize only once. Okay, so let's see how that looks like. So this is our demo. You already have it. So I'm importing a bunch of visualization libraries and whatnot. Actually, let me do this. I need extension off. All right, cool. All right. So loading the data set. So take a look. This is our friend from before. Miles per gallon is one column of the data frame. And then there's all different kind of features for different kinds of cars. And what we're interested in is horsepower. So we want to use horsepower and different powers of horsepower in order to predict miles per gallon. So the next thing that I'm doing here is I'm actually creating my design matrix. So I'm saying that, okay, go ahead and create X as the data frame that only has horsepower initially. Then I'm going to create horsepower to the power of 2 column. I'm going to calculate horsepower to the power of 2, to the power of 3, to the power of 4. So that's my design matrix. Now it has 4 different columns. Then what I'll do is I'll pull out miles per gallon from the original data frame. This is a mistake that you might make when you do modeling, to leave the target vector into the design matrix and just try to do the prediction. But you know that the actual target vector is one of the columns in the design matrix, so you can directly perfectly match. So make sure that you pull it out. The original data frame that you always get should not be the final data frame that you're using for the modeling purposes. So this is now going to be a series object. Let me actually go ahead and take a look at the head of X. So it has all of the things that we wanted. Then I'll take a look at Y 0 to 5. And so you basically see that these are horsepower, miles per gallons that we have. The data type is float. So I said that there is this function in scikit-learn that is called train test split, and it will do the splitting for us. One thing that I want to note here is note the differences in the size of the training set and also the test set. we want majority of our data to be in the training set because training is going to be the heavy lifting part. The test part is going to be a small percentage. So we really want to have a sample of the data that's small enough, but also large enough that captures the general distribution of the data. So we really want to kind of play the balance between having enough data points and having a representative set of data points in the test set. So this test set does not need to be big. Usually what I'll do is like 20%, 10% of the sample or the data frame to be in my test set. That's what we would do. So let's take a look at how I can use this function. So train test to split. The function takes your design matrix and also takes your target vector aligned. So it has to have the same number of rows. What it will do is it will try to actually split it into two parts based on what you're providing as the test size. So the test size is going to be a value between 0 and 1, which is the ratio of the data points that you want it to be in your test set. So what I'm going to do is my design matrix was X, my target vector was Y, right? And then I would say that test size is equal to, I'm going to put like 20% in the test size. There is this other notion that's called random state that I can pass to this function to make the function or to make the entire notebook reproducible. Because what this one is doing, train test to split, is it's going to randomly split the data points into two parts, right? 20% goes into testing, the rest goes to the training. What you want to do is you want it to be random, but you want it to be pseudo-random. You don't want to get different results every time. So you want to say that, okay, if I'm reporting the test error to like the certain precision, I want exactly to get the same thing, and I don't want to leave it to chance so that it's reproducible. So the way that we would do it is we would basically put a random seed in the randomization function. So we're going to go over this a little bit more in future lectures, hopefully. But this is what I'm providing. I'm just picking a number. The number doesn't matter. So I'm picking 100 for data 100. But technically, any number that's the same number that you're running, everything else is going to be basically be run based on the same number. So let's see what I'm getting. I'm getting something that looks like a data frame. It has the column names that I had, horsepower, score, and whatnot. It tells me that there's 313 rows and 4 columns. It looks like that it's also giving me another thing with like 79 rows. Then scrolling down, it looks like that it gave me a series object with the name MPG, only 313 type float, and a similar thing for a smaller set. So you can kind of see what I'm getting. I'm getting a portion for training. I'm getting a portion for the test, and then I'm getting respective labels. So let's just store it into the variables that then I can use later on so that the results persist. So I'm going to say xtrain. So that was the first thing. It was the largest chunk, right? It was 313. We want 80% of the data to be there. We want 20% of the data to be in the test. So I'm going to use xtrain, xtest, ytrain, and then ytest is storing the same thing. So calling the function, this is good to go. I can call it. Now everything is stored, right? Easy peasy. We don't need to do anything. We don't need to implement randomization ourselves. We just basically call this function. Now we have 2 data sets. So we can take a look at the sizes. So you see, I originally had 392 data points. So now I have 80% in training and 20% in the test. So let's actually go ahead and do modeling. So this is our friend from, well, reporting that as LM. So I'm saying that, okay, this model object I'm going to create, and I'll say lm.linear linear regression, right? So I'm creating the model object, but now I need to fit to the training data. Remember that every training is going to be done by the training data. Then I have the model, then I'll do the inference on the test data. So I'll say model.fit. What do I pass? Xtrain, and I'll pass ytrain, the respective thing. So I have the linear regression object ready to go. It has all the coefficients. So what I can do is I can go ahead and say, okay, model, go ahead and do the prediction on the training data. And then I'm going to compare you with the training ground truth labels. I'm going to do the same thing for the test. And then there is this function mean squared error again from scikit-learn that I can directly call, get the aggregated training error, get the aggregated test error, and I'm printing both of them. Let's take a look. 18 and 21. Is this expected? So like we always, as like engineers and ML scientists, we basically do a gut check. Like, is there something horribly wrong here? That 18 is less than 21? So the training error is 18, test error is 21. Okay, I'm gonna do the gut check for you, and you will basically follow the same thing every time that you're doing the modeling. This is perfectly fine. It is fine because, and then again, notice that we calculated mean squared error. Although the sample sizes were different in the training and test, it really doesn't matter because we were calculating average of the errors. But the average of the errors for the test data was more than the training data. Although we randomly distributed the data points between training and test, and we were expecting them to be the same. But the advantage that training data had, each sample had a say for the parameters, right? So the model was trained such that we do a good prediction on average for all of the data points. The model had not seen anything about the test data, so it could not actually perfectly match to the test data. So it is always expected that there's a little bit of a higher error on the test data because of the fact that it was not seen by the model. Okay, that's the gut check that you need to do every time that you do the comparison. How are we doing? Good? Sideways? Down? Too easy? Too difficult? Okay, so it's like easy stuff that are going to be practical. But it's going to get more interesting because I basically gave you some idea about the things that can go wrong. So let me show you an issue. I don't have it here, but I have it in the slides. So the issue is that I said that we can only use the test set only once, right? So what if like we're not satisfied with the result that we're getting on the test data? So can we go back and change anything about our learning rate? Can we go back and like add horsepower to the power of 5, for example? No, if we're not happy, we're stuck. So the thing that we can do is because we cannot go back, so I'm going to highlight it, that we cannot go back and adjust our model. What we're going to do is we're going to actually take another chunk, put it separate, and we're going to treat that as our internal testing. So every time that internally you want to know whether your model is ready or not, and whether you have to still continue doing feature engineering, whether you have to pick a different learning rate or whatnot, any kind of design decision. So up until the point that you're ready and you've exhausted all of the search that you wanted to do, we're going to do those internal testing on our internal test set. So I'd like to introduce that as internal test set, but the formal kind of name for it is validation set. So we're validating internally whether our model is ready or not. Once the model is ready, then we go and pass it to the test data. We do the check one time and we report the accuracy or the model metric on that test data only once. So that's kind of our solution for it. So again, our entire framework looks like this. We had the initial entire full data set. We split it into training and test. We said that, oh, like I can only use test set once, but what if I want to do more testing and have internal validation? Then the idea is that get your training data set, split it one more time. Now you have the training data set, which I'm going to call it training mini data set. I have the internal testing or validation set, and then I still have the test set that's separate, right? So now we have 3 chunks in our data. So let me go ahead and do that quickly for us here. So I'm going to just copy this over. And we're going to change a few things. So I'm going to do the splitting, right? But this time I'm splitting on not X and Y. I'm splitting on the training data. Because remember, the training data is the one that's being splitted here. X train, Y train. I'm going to give it another like 20%. So this is 20% of the 80% of the training data that we had. That's going to be validation. The rest is going to be in the actual training data. So I'm going to call this Instead of test, we basically have validation. So all the tests are now going to be my validation. And then instead of xtrain, now I have a different part, which is called xtrain mini that I'm going to use, right? So it's just basically reusing the same thing, but now I'm splitting the training data, and my output is actually going to be xtraining mini and xvalidation and the corresponding labels, so I can do the analysis on them. So let's take a look. How many samples I have now? I have 3 chunks. I have the original data set that's 313, the mini training data set that's like 250, and then I have a smaller set that's my validation set. So let's do something quickly. What I'm showing you here is that what if I go ahead and train different models with different degree polynomials of horsepower, so degree 2, degree 3, and degree 4, and I show you the result on how many data points that we had? It was 60 something, right, on the validation set. So on the validation set, we had 63 points. And I show you the result on the validation set. So why am I doing this? Because I want to decide what is the complexity of the model that I should use. Should I go with the degree 2 polynomial, degree 3 polynomial, degree 4 polynomial? So how many features do I want to use? Again, the reason that I can do it now here and do this comparison is that validation set is my internal testing. I would not be able to do it with the test data, right? But I can do it with the validation data. So look at the validation MSCs. So I have one validation MSC here that's like 12.4, another one 12.1, and another one 12.193, right? So which one is going to be a better model complexity that we can use based on the validation data? The one with the lowest MSC. So we make that decision, we move forward, use that model on the training data, and then we test it once on the test data, and we report the accuracy or MSC on the test data kind of separately. So let's actually go a little bit crazy, and let's go ahead and define this function that takes a degree and actually goes ahead and creates does the polynomial transformation of all different degrees. And I'm actually doing the range of 0 up until 18, right? So degree polynomial 0, 1, 2, all the way to 18. And I'm going to go ahead and say, okay, create the model, fit the model to that degree complexity, and return to me the validation error, right? So notice that that's validation error. That's the kind of thing that you can do. You can really go ahead and examine the model in and out in terms of the features, in terms of the hyperparameters that you're using for the training, and pick the one that gives you the best kind of result on the validation set. And that is the degree polynomial that you want to use. That is the hyperparameter that you want to use. So in this case, this is going to be kind of the visual for it. You see when the model complexity, so the x-axis is model complexity. This is kind of similar to the graph that we started with. So when the model complexity is 0, meaning that I have degree 0 polynomial, what is that? That's a constant model, right? So when I have a constant model, I have a very high validation MSC. So it's really hard to fit to the data if you just don't have any signal or you're not using any information from the data. And if, as you're increasing the model complexity, you're seeing that the validation error drops, but then you see that we're hitting this plateau area, right? And then there's this part starting from 11 that then it keeps increasing. Why is it increasing? Because when we're hitting 11, for example, the model can really perfectly overfit to the training data. Because it's overfitting to the training data, validation data does not have the similar features. It might not have similar noise characteristics. So that's why then your trend is going to be different. So you're not going to get like those kind of perfect predictions. And the model variance is just so high that like with the small changes, then you're seeing a high deviation. So that's why you're seeing all of the validation areas going up, starting from 11 all the way to 18. So this is the kind of thing that we use with the validation set in order to decide what's the good choice of a model and what's the good choice of the training moving forward, and what is the best model that we should package and send it to someone else so that they can test it on the test data. Because a lot of times the test data is not going to be internal to us. A lot of times in machine learning competitions, for example, the test data lives somewhere in someone's server. Grad students are going to actually experience this with the final grad project milestone. You just have the original like design matrix for, not the design matrix, but the input data for the test data, but you don't have the ground truth values to compare against. You just are sending it to some server. The server is going to run it. It's going to calculate your predictions on the test data. It will tell you where you stand in some kind of a leaderboard thing, right? So that's why it's really important to have this internal mindset of how do I think that the model is going to do an unseen data, and have your own version of unseen data actually, but there is always generally going to be fully unseen data sitting in some server when you're basically doing real world kind of analysis. So let me take a look at some of the few things. So I'm going to basically, I printed out all of the MSCs for different degree polynomials, so you can directly see that the MSC is plateauing, but you can see that there's a little bit of variation. But what I want to point out from these numbers is that when you're increasing the complexity from 6 to 7 and you're getting a little bit of an improvement in MSC, it's probably not worth the effort, right? So you're just spending so much on the model complexity that this is small kind of delta is not going to be worth it. So those are kinds of the decisions that people would make when they're comparing different, say, large language models. And speaking of large language models, we're going to have a fun large language model lecture coming your way in the last lecture of the course. So again, but we plateau-ish a little bit up until like from 11 to 12 that you're seeing that the value keeps increasing. If I go ahead and get the polynomial degree with the lowest validation error, that's going to give me 8. So that's like the lowest possible that we have. But again, it's just like whether that it matters after, what is it, after like degree polynomial 2 or 3, whether you really get such a huge improvement to go from 3 up until to the 8. That's also a separate discussion that we can have when we're studying model variance separately. Okay, going back to the lecture, we have a lot to uncover. This is a similar kind of plot that we'd seen. The validation error is going to, this is the same thing, like training error was always decreasing as the model complexity increases. There's a little bit of theory behind it that then if you keep increasing this model complexity a whole lot, like very large models and very complex models, then this training error might actually increase and then it's going to decrease. But so that's a separate story. But what I want to get at is this new gold line. This new gold line is telling you that there's this validation error that decreases. Initially, what we're expecting is that it's kind of generally going to be higher. It's going to have higher error than the training data, but it decreases with the similar rate up until the point that they basically diverge. At the point that they diverge, basically is the part that we're moving from underfitting to overfitting. And again, the sweetest spot is actually being very close or as close as possible to this dashed line that you see on the plot. So what we talked about a little bit is how can I actually go after controlling the model complexity? And we're going to see that in the second half of the lecture, but now you know what we're actually dealing with. So I want to talk a little bit about like one more advanced way of us doing training, validation, test to split, which is called k-fold cross-validation. You should actually do k-fold cross-validation properly in your housing project in the second milestone. But let me tell you about it. So when we were kind of doing in the split of the validation from the training data, we were basically looking at, okay, like I'm going to randomly sample 20% of the data points from the training sample and just use that as validation set. But the issue is that if I go ahead and show you here, is that, okay, like if I go ahead and just run this process, say 3 times, 4 times, right? Let me see. Why is it not working? if I keep repeating this process, but I don't set the random state. So I just specify that I want 20% of the data, and this is my training, and this is my test, and just let the process every time give me one random 20% of the data to be in my validation. What you're seeing is that we're seeing different errors, right? So we're seeing that, okay, like there was one time that we got the average error of 22. There was one time that we actually got really lucky, right? So when we got lucky, it was the case that, okay, the validation had very similar distribution than the training. So basically, by us optimizing the thing on the training, we kind of also optimize it on the validation data. But there is also this time that we were not so lucky, right? So the validation error is high. So there is variance, and we don't want to leave our testing process or our modeling process up to chance. So what we will basically do is we will basically do exactly the same thing, but more systematically. So the systematic thing is that, okay, this is what you'd seen. We don't want to leave it to just being lucky or not lucky and getting a good validation set or not. But what we would do is instead of saying that, okay, I'm going to get the training and validation, we would say that you want 20% validation. Why not take multiple 20% chunks from your training data? So if I have if I have my data set, say I have like 100 different samples. So there is the first time that I'm going to get the first 20%. I'm going to say that that's my validation. There's going to be the time that I'm going to say that, okay, the second 20% is going to be my validation. Everything else is going to be training. And then I'll do the same thing. So every data point is going to have a chance of sitting in the training data 4 times. And it's going to have a chance of being in a validation data point or validation set once, right? And this is the way that we're not leaving it to luck. And effectively, this entire modeling pipeline will basically look at the average of what's happening over multiple different rounds of modeling. So what I described was that, okay, if I'm saying that I'm picking 20%, I'll say that, what if I pick the first 20%, second 20%, third 20%, fourth 20%, or the last 20%? And this 20% is just a randomly picked number. Like you can do 10%, right? If you do 10%, then how many chunks do you have? 10, right? So if you do 10%, then you're going to have 10% chunks. We'll pick it in a way that they basically divisible by the thing, but by the size and whatnot. But effectively, that's what we're trying to do in this case. We call these chunks fold. And we call this process K-fold cross-validation. And where does K come from? K comes from the fact that how many chunks do you have? In this case, when I'm looking at 20%, I have 5 folds. This is 5-fold cross-validation because I'm basically giving a chance that all the data points are able to basically be sitting in the validation set only once. Okay. There might be a hypothetical semester that there might be one question from the audience that you might ask me that, okay, like Nargis, what if this data is sorted? So you're always picking like the lowest set of values as your chunk 1 and then the second lowest set of values for chunk 2. Isn't it going to be confusing for the model to just like arbitrarily kind of pick numbers or pick set of values for validation set and then the rest for training? So it's going to be hard to kind of manage that kind of bias. The answer to that is you first randomize the entire data set. So you randomly shuffle the whole thing. Then you're going to pick the first 20%. Then you're going to pick the second 20%. So you really make sure that there is no bias in any way that you're ordering the data. Therefore, picking the first 20% is literally going to be picking a random set. So there's not going to be any structure. So we talked about these chunks. I have these 5 folds. If I have 20%, for example, and this process is called cross-validation. So in the K-fold cross-validation, what we'll do is before anything, randomly distribute or randomly shuffle the entire training set that we have. Then we divide our data set into K folds. Let me highlight it. We divide the data set into K folds, right? That's the first piece, which is like the thing that you saw here. Like I'm kind of artificially, not artificially, but like hypothetically dividing the data sets into K number of folds. And then what I'll do is I'll basically pick one fold. That one fold is going to be validation fold. Everything else is going to be training, right? And then I'll basically compute train the model on the training data, compute the error on the validation data, and then I'll move on to the next fold, and next fold, or the next model, and next model. And what we'll do afterwards, once we ran all of the thing on all of the K folds, we basically take a look at the average error that we got over all of the validation sets that we had, right? Let me visually show you how that looks like. So the first time, for example, the example of 5-fold cross-validation, I'll leave let's assume that I'm basically chunking from the end of the sequence. So I'm picking everything in the beginning as a training set. The last 20% is going to be my validation set. So what I'll do is I'll train the model on the lighter blue area, and then I'll compute the mean squared error on validation fold 1, right? So this is the validation set 1. Then I'll do exactly the same thing for everything else. For everything else, what I'll do is I'll basically train the model on the lighter blue area, and then do the MSC calculation. This is the validation error 2 that we're recording. Same thing, I'm training on this part, recording it here, and recording the error here. And the total validation error that we're going to report, because now we have 5 numbers, right? So which one of them should we pick? Remember that the whole idea is that previously, if we were just leaving it to one validation fold, there could be a lot of biases, or we're basically randomly might get lucky to get a good validation set or not get a good validation set. So here we're saying that I'm going to exhaust all possible options of having a validation fold being structured differently. So with 5-fold cross-validation, I'm seeing 5 different validation sets. And the total validation error that we're going to report is going to be the average of all. This is very systematic. It's very unlikely for this process to introduce any biases, or anything is going to be left to chance, because every data point had to say in the training process 4 times and had to sit also outside for the test error or validation error exactly once. So every possible kind of scenario is calculated. Not every possible scenario. So the more folds you have, kind of the better process, the better process you will get, but it's also better than just having one fold sitting outside. So visually seeing, how is that going to look like? So the full data set, we're going to divide it into training and test. We don't test at all. So the test is going to sit literally outside. So now with the training set, previously we would just go and divide it by 2. We get the validation and we get the test. But this time we're going to systematically run K-fold cross-validation. So we're going to have K different scenarios. So this is scenario 1, scenario 2, scenario 3, scenario 4. This is 4-fold cross-validation example, for example. We will have 4 different models, because every time that you have a training set or mini training set, you're going to have models. So I'm going to call this model 1. For a combination of these 2, I'm going to have model 2. For a combination of these 3, I'm going to have model 3. For these ones, I'm going to have model 4, right? On each one of those models, then these validation sets are going to give me a validation error. So this is going to give me validation error on model 1. This is going to give me validation error on model 2. This is going to tell me validation error on model 3. And this is going to give me validation error on model 4, right? Let's assume that you wanted to pick the best hyperparameter for a model. So say, for example, you wanted to pick learning rate. So you want to say, okay, learning rate of 0.1 is better, or 0.01. So in those cases, you basically run K-fold cross-validation with the assumption that you want to pick learning rate of 0.1, right? You basically get all of these validation errors based on that learning rate. You will calculate average of all of these ones. So you're going to basically calculate average of all of the VMIs, right? And then this is going to be a value, right? You get a value for the learning rate of 0.1. You're going to get a value for learning rate of 0.01. The one that's better is going to be a better hyperparameter. Same for any kind of feature engineering that you want to do, or anything that you want to change in the modeling process. Okay, I talked a little bit about this idea of hyperparameter. You know what hyperparameters are at this point. So we generally use this process to do hyperparameter selection. Hyperparameters are model complexity, learning rate. We're going to see regularization penalty and things like that. So all of these are hyperparameters that previously we would just come up with like a picked value, right? Or we were not systematically setting up those values, but now we have a proper system of seeing how we can tune hyperparameters kind of at least systematically. So again, in all of these cases, what we would do is we would say that, okay, I'm gonna go ahead and have some guesses. In the case of learning rate, I was giving you the example of 0.1 and 0.01. You're gonna have all of those guesses. You're gonna run cross-validation for each one of those guesses. Remember the cross-validation error, and then select the hyperparameter with the lowest cross-validation error, and that will be your selection, and then you will move on. For example, if my learning rate is 0.1, 1, and 10, effectively I'm doing one full cross-validation with the alpha of 0.1. I'm going to do one full cross-validation with alpha of 1, and then another one with alpha of 10, right? And notice how many models I'm creating. Notice how many validation errors I'm calculating. Notice how many models I have to train. So there is a little bit of an overhead, right? Because I'm for like alpha of 0.1, I'm training like 3 models for 3 full cross-validation. So for k-fold cross-validation, you're training k models. But it has the benefit of at least like systematically telling us like how we can make sure that we do a hyperparameter selection properly. So, okay, I forgot to say, if I calculate all of those averages and those are cross-validation errors, we pick the hyperparameter that has the lowest cross-validation error, which in this case is alpha of 0.1. Okay, I was rushing to get to this so that you can get some practice. If I want to select the best polynomial degree for the model, and I have 5 possible options, right? Say degree 1, 2, 3, 4, 5. And I want to do 4-fold cross-validation. K is equal to 4. What is the question? How many times do you need to compute MSC? Like if you had the MSC function and you had to call it, how many times would that be invoked? There is a good question of how can we come up with guesses for like learning rates and whatnot. There's no best answer for it. Like there's the idea of selecting hyperparameters or selecting model complexity. These are really deep in ML theory. But like practitioners would generally have a bunch of different like local search options that we would say, okay, like we do 0.1, we do 0.01, and all of those things, like which one got better, then I'm going to have more options there, like try to optimize it kind of iteratively. Very good question. 266, that's good. That's a good number. Please also come to office hours. It's good that you're coming to lecture, but come to office hours. It feels lonely. I moved my office hour from Tuesdays, not just for this week, to be tomorrow 2 to 3. So if you're free, come by. We can have coffee. I have coffee machine in my office. Let's see. 20 is the right answer. Remember, like all of those, each one of those iterations, it gives me a model. A model needs to be evaluated on a validation error, on a validation set using MSC. So we calculate it. So 4 times 5 is going to be 20. That is right. How many times do we train a model in the same scenario? 5 hyperparameters or 5 options, and then 4 folds or 4-fold class validation. How many models are we training? Okay. I think the right answer is not on this slide. Anyone can guess what's the right number is? No, not one. But one added to something. One of these options is correct, plus one. Okay, let me tell you. So 20 is close. We are training 20 models. Like every time that we have a validation error, like what are we using for getting that validation error is a new model, right? So we train that new model. But I want to tell you one thing, going back to this guy right here, is that, okay, we do all of these like cross-validation and stuff, it's cool, right? What is the final model that you want to package and send out to someone to test it on the test set, right? So what we would do is we will use this process to do model selection, right? We say that, okay, degree polynomial 2 is good, and then my learning rate of 0.1 is good. So those are my selections, right? Then I'm gonna put together all of the validation, like basically go back to my training set and train that model entirely. Now I don't need to have a validation set separately because I already made those decisions. I don't need to test anything internally anymore. So I basically go back to the training set, train a model with those hyperparameters. That's the model. Then I pass it to the test set to be tested, right? So it's 20 plus 1 because there's that final packaging that we have to do because otherwise they have to pick and choose between these four like pseudo good kind of models. And I say pseudo good because they did not have enough data because you're like separating part of the data from them. So you just really want to make sure that you use all the data that's available to you for the entire training process. Okay, that was a good exercise. I like that we did not have the correct answer on this slide. It was a teaching moment. That was good. We talked about this already, and now you deserve a 2-minute break so that you don't have to listen to me all the time. What's going on? I promise you I had a nice thing here. Not working. We're gonna be back 6:04, or I can give you 6:05. Go drink some water, walk a little bit, but come back. Please come back. All right, let's restart again. So this is the second half of the lecture. It is really practical and it is really fun. It's kind of eye-opening, and hopefully it's also a motivation for you to go and take a look at some of the optimization courses we have in our curriculum, or just to study on your own. It's just generally good to be data scientists with like solid foundation. That's what we're trying to build here. So I'm not going to go into the depth of the optimization behind this next piece, but nevertheless, it's like beautiful. So let's talk about where we are. So we've been talking about the fact that, okay, like there is this notion of seen versus unseen. We figured it out. Then there's this other issue that we wanted to find this sweet spot to find out like at what point are we overfitting to the training data or not, and how to control complexity, right? So overfitting effectively means that we're trying to control complexity in a way that the model is complex enough, but not too complex. So again, I keep telling you this idea of this dashed line, that we really want to find some notion of like what's the right place for us to kind of distinguish between underfitting and overfitting and have a good performance both on the training data and also on validation data that we have. The idea that we're going to use here is that we would say that, okay, so for controlling the model complexity, actually, let me go back and say one more thing. The whole reason that I had this variance thing was that the variance will keep increasing as you increase model complexity, right? But you can't really look at the variance in isolation, because there is just to some point that increasing the variance is good. There's a certain point that increasing variance is not good. There was this other notion that how can we like intuitively think about this variance thing? So one way for you to think about how you can figure out the model's variance is going to be high or not is going to be looking at the model. So look at the model. So I have this prediction y hat that's calculated based on theta 0 plus theta 1 times feature 1, theta 2 times feature 2, and then all the way to theta p, right? So hypothetically, do this exercise with me that you think about this theta 2. If the value of theta 2 is a large number, so for example, it's 10 to the 6, right? Versus the case that this value is 1. In which one of these cases would my model have a high variance? The first one, 10 to the 6, or the second one, that's 1, the weight is 1. So in the case of 10 to the 6, the model variance is going to be higher. And I gave you the intuition behind it in the beginning of the lecture. I basically said that if by a small change in the feature, you're going to suddenly get a different value in the output, then that's a large variance, right? So this is what we're trying to avoid in the model, that we are trying to generally avoid having not only that the number of features is important, but also the size of those parameters for those features are also important. So we're trying to have this notion of I want to have limited number of features, but I also want to make sure that the features that I'm using, the parameters for them are also reasonable and they're not huge, so that they drive this model variance to be a very high variance model. So the way that we're actually going to do it is that we would say that let's assume that I have a limited budget. So there's a budget for the model, and that budget is the model variance. So I would say that I can tolerate this amount of like variance in my model. Just go ahead and split it between all of the features that you have. You do whatever you want to do in terms of saying that, okay, like this model, this feature can get the parameter value to be like, for example, 1, this other one needs to be 0.1, this other one needs to be 0.2, so that looking at all of the features together, all of those parameters together are just spending less than or equal to the total budget that I allocated. So think about that variance that I can tolerate as the budget for the model. So the whole idea is that in regularization, what we would say is that we will take a look at some notion of magnitude of these parameters. So I would say that we're putting a limit to the magnitude of these model parameters. And that's the way that we're going to control the variance. So I'm going to mathematically show you how we're actually do this budget allocation and budget limiting, and like how I would interplay with the actual parameter values in the next bit. So This budget thing, if you think about this budget as some number Q, and we're going to basically play with that, and we want to measure some magnitude, some magnitude of the parameters that we have, and make sure that looking at the magnitude of all of the parameters that we have in the model altogether, they don't exceed the budget that we have. One way to implement it, or the simplest way to implement it, is that go ahead and calculate the absolute value of the parameters. The summation of those absolute values should not exceed the budget Q that I allocated initially, right? This seems fair. So it basically says that if one feature is just so important to you, just allocate most of your budget to that specific feature, but then it's going to come at the cost that the rest of the budget is going to basically be split to the rest of the parameters that you have in the model. And that's kind of the way that we're controlling the complexity. The model is now total have that Q budget, so it needs to really kind of think about prioritizing those features. It will kind of also do the feature selection in a sense. So basically say that, oh, this feature is just so important that I want to spend so much budget on it that it's not worth spending any budget on any other feature, right? So that's the way that it will reduce the number of features that are kind of participating in the model, but at the same time, it will make sure that the magnitude of all of those features are small, or those parameters for the features are small, so that I don't have the situation of 10 to the 6 as the parameter associated to a feature that derives the variance to be super high. So these are the two notions that we're going to use. So let me tell you how that visually looks like. So when we were looking at the gradient descent, remember that we had this lost landscape, right? So in this lost surface, assuming that I only have two features, because that's the only way that I can manage visually showing it here, say that I have theta 1 and theta 2 as two features, and I don't have a bias term. This is also kind of a lost landscape where the darkest area has the lowest loss. So the idea that we have is we want to make sure that we run gradient descent. We start from somewhere randomly, right? And we take the derivative across partial derivative with respect to theta 1, with respect to theta 2, find our way down in this path up until the point that we get to the center of this part, right? So what we would say is that if we don't have any regularization or any kind of budget issue, we should be able to find this kind of solution by following the gradient descent path, and then we'll get a set of parameters. So this theta hat is a set of parameters, which is like equal to theta 1 hat and also theta 2 hat. That is optimal. It has the lowest loss, and everything is good, and everything is nice. But again, we know that the theta 1 and theta 2, we can really go and overfit to the entire training data, and the model can be complex, not in terms of the number of features this time, but in terms of the magnitude of these features, right? Imagine that theta 1 and theta 2 can be very large values, and that's the thing that we don't necessarily want. So what we would do is we would constrain it. Let me visually show you what constraining is going to look like. We're constraining the magnitude or the summation of the magnitude of these two features subject to the total budget of having Q. And that's going to be us living in this diamond, right? What is this diamond? So let me write this for you. So in two-dimensional space, effectively rewriting the same thing, P is equal to 2, right? And then we also know that theta 0 is equal to 0 in this case, for example. So effectively rewriting that is going to be that theta 1, absolute value of theta 1 plus absolute value of theta 2 has to be less than or equal to, less than or equal to our Q, right? So what are those dimensions on the diamond thing? So this, at this point, when theta 2 is equal to 0, the maximum that I can get on that corner is going to be Q, right? This right here is also going to be Q. This part right here is going to be negative Q. This right here is going to be negative Q, right? So if I want to actually have a model that is constrained, so you cannot leave this diamond thing. You have to live in this diamond, right? That's the constraint. That's the budget. You don't have any more budget. So you can't exceed this kind of variance that I have, right? Where would you go? What would be the optimal solution subject to this constraint? We effectively want the darkest area in this diamond. So probably here in this case is going to be the darkest area is going to be in this top corner right here, right? So what's happening is that when we are kind of defining this kind of budget and this kind of limitation, and we're trying to make sure that, okay, like the variance cannot grow, the parameters cannot grow. What's happening is that the parameters that we're going to end up having are going to be not global optimum parameters, but there are the parameters that are going to be regularized parameters in a way that they keep the model complexity controlled so that like it's not overfitting to the best case of the training data. Hopefully we're in search of finding like what is a good kind of point, which is that dashed line that we had initially, right? So this is kind of the general idea. What I want to also point out is that this budget is very important because it plays an important role. So for example, when the budget is small, so compare this one with this one, right? When the budget gets smaller, I'm more constrained, right? When I'm more constrained, it's more likely that I'm going to be far from the optimal theta value, right? So for example, in this case, I was in this like kind of second tier dark blue area, but when the theta, when the budget is smaller and Q is small, then I'm actually going into the fourth tier kind of thing. So my model is not going to be as good of a model, but then this is just so much budget that I had, like there was nothing else that I could use, right? If the model, if the budget grows, effectively what you're also seeing is that like you can basically get as close as possible to kind of the global optimum or the global solution that you wanted. Up until the point, actually, let's do a couple of Slidos, and then I'll come back to that. So based on this kind of intuition that I visually showed you, how does the size of the Q or the budget relate to the model complexity? When you're increasing or decreasing, which one is giving you a more complex model with higher variance? Which one is a lesser complex model with low variance? I'll wait for 200. Go. Okay, good. So small Q leads to simple model. So what's the smallest you can go? You can say that there is no budget, like sorry, Q is equal to 0, right? So you will basically get a constant model or something, or you're gonna be predicting 0 every time, right? So in those cases, what we would say is that, okay, the model is just super simple, it's not accurate, versus like the case that when the Q is large, it can grow as large as possible up until a point that it actually has the optimal solution inside it. So it might be kind of as if that you did not have any real budget for it because the budget was very large. So that's kind of the effect that we're seeing. When we have a small, then when we have a small Q, when the budget is small, the model is going to be simple. When it's larger, the model is going to get more complex. Again, this is the visual for me to show that when the budget is very large, it's just not going to be impactful. So you're not regularizing or limiting the model in any way because your best solution is also within the diamond, and you're basically leaving with what the training data is telling you. Next question is that if we pick a very small value of Q, what kind of model do we have? I kind of gave you a hint about it. It's a model that always returns 0, a constant model, OLS, or something else. Again, in the case that it was large, it was technically OLS. It was just the optimal solution. But what is it in this case? Okay, in this case, 2 options are correct. So it can either be a constant model if you have the bias term, or it can just be a model that returns 0 if you don't have a bias term. And the reason being is that, again, the same thing. So if we basically have a constant, have a bias term here, when all of the parameters are going to be equal to equal to 0, then everything else is going to be zeroed out. So the model is going to be a constant model, always predicting theta 0. If we don't have theta 0, it's always going to actually go ahead and predict 0. So this is kind of the visual of what's happening when we're basically having underfitting. We have a small budget, we have a small diamond, versus when we have overfitting, that means that this budget is large. And what we're trying to do, as you might guess from the two sides of the spectrum, is that we want to find the right size diamond, right? So the right size diamond is actually going to give us what this dashed line is exactly going to be placed. So let me tell you exactly the objective function that gives us that. So we have been like looking at this visually, but like looking at it mathematically, and in terms of what kind of loss function am I optimizing under the constraint that I have to actually satisfy this budget thing, is a new loss function that you're going to learn today. So there's the first thing that from OLS you learned, that we're minimizing mean squared error. That was a risk function. So this is basically calculating how good we're fitting to the training data. But now I'm saying that not only that I want you to fit good to the training data, but I want you to fit such that you also meet this condition, that the summation of these absolute values of the theta i's does not exceed the Q budget that you have. This is called L1 regularization, because this constraint that we're putting is called a regularizer term or a regularizer condition that we have. And it is L1 because what you're seeing in the left-hand side is kind of L1 norm of the parameter vector. That's why it's called L1 regularization. So for the reasons that for the purpose of data 100, I'm not going to go through the details of how I can actually solve this kind of complex condition, because I'm minimizing mean squared error, but I'm putting a condition. So the idea is that here we're using Lagrangian duality, which is a topic of an optimization course. I'm not going to go into it. But the way to optimize this entire equation under that condition is that combine the two terms together. So this first term right here is coming from the MSC, right? So go ahead and grab MSC. The second term here is saying that go ahead and get your condition, so the left-hand side of your condition, but instead of directly saying that, oh, I have this budget specifically and treat that budget thing as a hyperparameter, you would say that I'm going to give you kind of a weight value, or how much I want to value, or how much I want to constrain the weights. And in aggregate, these two terms are going to make up your cost function right now. Again, one more time, look at this cost function, or this general risk risk function that we have. Part of it, like the first part, is that we want to fit good to the training data. That's not changed. That was always the case in OLS. The second piece is that we're saying that I'm also going to penalize you if you pick large parameters. And looking at the summation of absolute values of all of those parameters, I'm going to penalize you. But what is that penalty factor? We're saying that we're calculating summation of those absolute values. We're multiplying it with lambda, which is a regularizer hyperparameter. So it is a hyperparameter because it has some relationship with the Q. So when Q is small and the model is so constrained, what does that mean? That means that we really want to penalize if the model picks a large parameter, right? So in that case, what we would do is we will pick a very high or very large value for the lambda, so that effectively looking at these two terms playing a balance for like figuring out what should be the collection of the parameters for the model, it's going to heavily penalize the model if it picks a large parameter. So it's going to actually shrink the parameter values, which is going to come at the cost of having not good prediction on the training data. But overall, looking at the balance between these two terms, it might actually be worth it at the end. So think about how these two are going to balance each other and how they would relate to how lambda is actually relating to the budget thing that we had. So this is our new augmented objective function that we're trying to solve. And again, what I talked about was that the first piece is optimizing for MSC. The second piece is to make sure that the parameters are small. And there's the same notion of the budget that we still have here. And again, there is a negative or inverse relationship between lambda and the budget. So if the lambda is a large value, say, for example, this is a high value, I don't want to put a number, but like say that it's a very large value, this entire objective function is going to be driven entirely based on the second term. So basically it's going to ignore everything about the training error because I'm just going to penalize you so much if you have any small value even for the parameters. So it will drive all of those parameters to zero so that it doesn't incur that kind of a high loss, because anything that it puts here for the theta parameters is going to be multiplied by this large factor that I put, right? So what does that mean? That means that when lambda is a large value, my budget was very small. So that's how the inverse relationship exists with the budget and the lambda value. But it's also vice versa. If lambda is equal to 0, what would you get? No regularization, right? That's like your normal loss function based on mean squared error, right? So that's how basically we're managing the budget or not managing the budget based on that thing. So there's multiple things that I want to cover here, which is like the implementation of it. So the implementation is pretty quick and easy. We call this model LASSO model. So did I have it here? Yes, LASSO model. It means least absolute shrinkage and selection parameter. It tries to drive parameters to be small. And then at the same time, it tries to drive some of them actually to 0 so that you're also doing parameter selection as well. So the way that we call this model is we use the linear model kind of framework. So we call linear model.lasso. We pass the lambda value. So the parameter, the argument is called alpha. So for example, here I pick alpha to be equal to 1. We fit it, we get the coefficients, and you look at the coefficients, you see all of the coefficients are small values. So now this is a huge difference. So small coefficients are basically a simpler model. So what you're also seeing is that if I actually go ahead and increase my alpha value, say, for example, I pick alpha of 10, the small values that I had previously, so for example, looking at this small value, they're going to get even smaller up to the point that now it's actually literally 0. This is the part that is actually doing feature selection. It says that this feature is not worth it. I'm just going to put the theta value next to it to be equal to 0. I'm not going to use it. So this is LASSO model is actually going to do feature selection for you under the hood. This is what you can kind of use for your project A and also project B every time that you're trying to kind of decide about like which features do I select. So you can use LASSO as a way of doing feature selection as well. So the next thing that I want to say is that the magnitude of all of these features are important. So for example, if you take a look at, for example, horsepower to the power of 8, this is a very large number compared to just the horsepower that is 150. So what we also need to do is to remove the impact of the features themselves so that when we're comparing the feature, the parameter values, we're comparing apples to apples. Because for example, if you take a look at, okay, so here, the parameter for horsepower is just this small number, and the parameter for horsepower to the power of 8 is this even a smaller number. What does that mean in aggregate? Because partly this thing here is smaller because the feature value is so large. So what we also try to do is to just go ahead and do a standardization. So standardization means that we remove the mean, we divide it by a standard deviation of the column, so that like features are living in the same scale. So then it makes sense to just do the feature selection using the LASSO regression. So the last thing that I want to talk about is quickly another type of regularization. So the idea is exactly the same, except for this time, instead of using L1, I'm using L2 norm of the vectors, meaning that instead of calculating absolute value of the theta i's, now I'm summing up the theta I squares. So every time that we taught L1, we also had the notion of L2. It's exactly the same thing. Instead of me living in a diamond, I'm living in this circle shape. But still, everything is exactly the same. So the cost function under the constraint of the budget, similar scenario. I will combine it with Lagrangian duality. So you will see that now the second term now has the hyperparameter of the regularizer hyperparameter. Then what we basically do is that this objective function, this augmented objective function has the part that tries to minimize MSE versus the part that tries to simplify the model, and this is called ridge regression. So similar scenario. So we call ridge this time. We pass lambda. So lambda here is equal to 1. We fit the model. We get the coefficients. You take a look at the coefficients, and the coefficients are small, but not as small as what we saw in LASSO regression. So in LASSO regression, it was shrinking to the point that it was actually driving some of them equal to 0, so we can actually do feature selection as well. So here it will do the control a little bit, but it will actually not drive them to 0. It will drive them to be as small values. But why do we actually use ridge regression and not LASSO regression? This is the last piece. I'm not going to prove it, but if you use ridge regression, no matter what your design matrix is, whether your design matrix is full column rank or not, there is a closed form solution. There is a unique solution that is closed form that we can drive it. So this is why sometimes ridge regression is going to be preferred, because sometimes training on a loss surface that only has one global minimum is easier than just to deal with like a very complex loss landscape, which has a bunch of different global minimums. Or a bunch of minimums that are non-unique. So this is going to have a unique solution. There's closed form solution for it. You don't need to memorize it, but just know that it exists, and that's part of the reason that we use it. And I'm going to leave you with this one. Summary: OLS, ridge regression, LASSO regression. The reason that we use each one of them: LASSO doesn't have closed form solution. Ridge regression does have closed form solution. Most of the things that we covered today, cross-validation and also regularization, are very important stuff, very practical. So watch this lecture one more time before you do project A2 and even possibly project B, because these are practical stuff that you have to really remember every time that you're doing a project. All right, thank you for coming. We will see you back on Thursday.